Hello and welcome back. In this video, I want to discuss the next major advancement that physicists had made towards understanding the photon theory of light. And this next major advancement came through studying something called the photoelectric effect. So the photoelectric effect was first observed by a man named Heinrich Hertz, who was attempting to experimentally verify Maxwell's theory of light. And basically what Heinrich Hertz was attempting to do was create a wave which he knew was made of electric and magnetic fields, and then show that these waves obeyed all of the same laws that light obeys. So for example, these waves will obey the law of reflection in Snell's law. And the way that he did this is that he needed to create a wave which he knew for sure was just electric and magnetic fields. And so the way he did this was that he ran alternating currents through a coil. So he had this coil, and then he generated this sloshing current inside this. And this created an alternating electric and magnetic field, which therefore created an electromagnetic wave. And because this electromagnetic wave was not in the visible form of light, he had to come up with some way to detect this. And the way that you detect something like this is by using what's called a pickup coil. So the idea is that as this electromagnetic wave passes through a coil, it will induce a voltage inside this coil. And to measure this voltage, for some reason, and I actually don't really understand why, he hooked up the two ends of this coil to something that's called a spark gap. So the idea is that if there is a voltage inside this coil, it'll create a spark across this gap. And you can actually kind of measure this voltage by increasing or decreasing the distance between the two ends of this wire. And the way you do this is by usually having some kind of adjustable screw that shortens this gap. So you can bring these two ends really close together, or you can space them out really far. And because Hertz was using a spark to detect the voltage inside this pickup coil, it was obviously really nice if he could turn off the lights in his lab. That way he could see the sparks. But when he did this, he made some kind of very strange observation. What he found was that if he turned off the lights inside his lab, he had to reduce this gap. In other words, it was harder for a spark to form across the two ends of the wires if the lights in the lab were off. However, if we turned the lights in the lab on, a spark more easily formed across the two ends of the wire. And at the time, he didn't really know why this was happening, and there wasn't very much interest in understanding this. However, in 1902, another physicist named Philip Leonard decided to look into this a little bit more closely, and he performed a series of experiments on this phenomenon, which is now called the photoelectric effect. So, to measure the effect that light has on an electron's ability to jump from one metal surface to another, Leonard placed two metal surfaces close to each other, and then he shined one of those metal surfaces with a bright beam of light. He then connected those two metal surfaces together with an ammeter. So the basic idea is that if this light caused any electrons to jump from one metal surface to the other, this would create a current which could be then measured with the ammeter. And when Leonard did this, he varied the intensity and wavelength of the light and found some very important results. The first thing he found was that the current that flowed from one metal plate to the other increased as he increased the intensity of the light. So in other words, if he shined a really bright light on the metal surface, that caused more electrons to fly from the surface. The second thing he found was that no current would flow from one metal surface to the other if he used a very low frequency of light. So if the wavelength was very large, then no electrons were scattered from one metal surface towards the other metal surface. The last thing he found was that at very, very high frequencies, changing the frequency of the light didn't seem to really matter anymore. So if you're at a very, very high frequency and you double the frequency, then that really doesn't have any effect on the current that's flowing through the circuit. So at some point, the current that was flowing through this didn't depend on the frequency anymore. And to measure the kinetic energy that these electrons had when they left this metal surface, Leonard connected the two metal plates to opposite ends of a battery. And the basic idea is that by connecting these metal plates to a battery, he could create an electric field which opposed the motion of the electron. So effectively, he's creating this barrier that the electron has to overcome to move from one metal plate to the other metal plate. So the idea is that if the electron doesn't have enough kinetic energy, as it moves against this electric field, the electron will slow down and eventually it'll turn around and head back towards the original plate. However, if the electron has enough energy, it will overcome this barrier and it'll fly over to the other plate. And we call this metal plate where the electrons are emitted from the emitter, and the metal plate where the electrons wind up is called the collector. And actually, I'm just noticing this now, looking at this picture. These electric fields I have drawn in here are pointing in the wrong direction. These electric fields should point towards the left, since they're creating a force on the electron which opposes its motion. It points towards the right. And the reason these fields should point in the opposite direction is because the electron is, of course, negative. So we can use conservation of energy and electrostatics to relate the kinetic energy that the electron has when it leaves this metal plate to the voltage between the two plates. So the idea is that if the electron leaves this plate with just enough kinetic energy to make it over to the other side, then all of that kinetic energy that the electron has when it leaves this plate will have been converted into potential energy by the time the electron makes it to the other side. So we can say that the initial kinetic energy is going to be equal to the final potential energy that it's converted into. So the kinetic energy that the electron had when it was emitted from the plate is going to be converted into electrostatic potential energy. And remember, we can describe the change in the electrostatic potential energy in terms of the voltage difference using this formula right here. So this is the voltage difference between the two plates, and this is the charge of our particle. So we have that the kinetic energy that the electron had when it left the plate is going to be equal to the charge of the electron times the voltage of the battery. And when Leonard performed this experiment, he found that the electrons that were emitted from the metal plate had all sorts of different energies. In fact, not only will these electrons have different energies, but they might fly off of the metal plate moving in different directions. And because of this, the relationship between the voltage and the kinetic energy was very complicated. So we couldn't write down a simple expression that related the kinetic energy that these electrons had to the voltage difference between the two metal plates. However, Leonard slowly increased the voltage between the two plates until the current finally stopped, and he called this voltage the stopping voltage. And the significance of this stopping voltage is that this voltage is going to be related to the maximum kinetic energy that an electron can have when it leaves the metal plate. And when he did this, he found that that stopping voltage was linearly related to the frequency of the light that was shining on the metal plate. However, it didn't depend at all on the intensity of the light. So if Leonard increased the brightness of the light that he shined on the metal, that would increase the number of electrons that flowed from one plate to the other, but it wouldn't have any effect on the kinetic energy of those electrons. However, Leonard found that if he increased the frequency of the light that was shining on the metal surface, this increased the kinetic energy that these electrons had. And remember, it had kind of a complicated relationship to the current. If the frequency was really low, there was no current that was measured, and at very, very high frequencies, the current was basically independent of the frequency. Of course, it's not at all surprising that light might knock some electrons off of a metal surface. After all, Maxwell says that light is nothing more than electric and magnetic fields. And we know that electric and magnetic fields exert forces on charged particles. However, Maxwell's equations fail to explain why the kinetic energy of the electrons that are emitted from a metal surface increase linearly with the frequency of the light. Secondly, according to Maxwell's equations, the intensity of the light is directly related to the strength of the electric and magnetic fields in the light. So according to Maxwell, the kinetic energy of the emitted electron should increase as you increase the intensity of the light. However, that's not what Leonard had seen in his experiments. And in 1905, Albert Einstein came up with a very simple explanation to explain Leonard's results. And the basic idea behind Einstein's theory was he said, well, the electrons that are emitted from a metal surface when you shine light on them increase linearly with the frequency of the light. So that means that the energy that the light has is somehow increasing linearly with frequency. And Einstein also knew that Max Planck had found out that the light that was emitted and absorbed from a black body came in packets of energy that were given by this formula here, Planck's constant times the frequency. So here this energy also increases linearly with the frequency. So what Einstein hypothesized was that the electrons in the metal surface could only absorb light in packets that had energy equal to Planck's constant times the frequency. And he called these little packets of energy quanta. And we can actually use Einstein's theory to predict the relationship between the stopping voltage and the frequency of light. So the basic idea is that Einstein's theory says that the electrons inside the metal will absorb the light in packets of energy that are given by this formula here. So Planck's constant times the frequency of light. And then that electron is going to have to do some work in order to escape the metal surface. And we denote that work with a capital W, and we sometimes call that the work function of the metal. So the kinetic energy that the electrons have when they leave the metal surface will be equal to the energy that the electron gains from the light minus the work that the electron has to do to leave the metal surface. And recall that the maximum kinetic energy that the electron has is related to the stopping voltage. So the idea is that at the stopping voltage, all of this kinetic energy will be converted into electrostatic potential energy. So we can set this equal to the electrostatic potential energy at the stopping voltage, which is given by the charge of the electron times the stopping voltage. So we can set that equal to Planck's constant times frequency minus the work function. And if we now solve for the stopping voltage, we see that the stopping voltage is equal to Planck's constant divided by the charge of an electron times the frequency of light minus the work function divided by the charge of an electron. And this is an extremely important equation. You definitely want to know this one. And as soon as Einstein saw this formula, he knew for sure that he was right, because he could see that the slope of the stopping voltage versus the frequency should be equal to Planck's constant divided by the charge of an electron. And because these two numbers are constants, he could calculate what that slope should be. And he found that that slope was exactly equal to the slope that Philip had measured for the stopping voltage versus the frequency. And this was an extremely important result, because this was really the first time that somebody had used this idea that light was absorbed in packets that had energy equal to Planck's constant times the frequency outside of the black body problem. Before this, people had assumed that it was the walls of the black body that absorbed or emitted light in packets that were equal to Planck's constant times the frequency. People didn't think that that was a general property of light, but for some reason that was a property of the black body. So this was an extremely important development for this photon theory of light. So after this, people started thinking that light carries these little packets of energy that were called quanta. And the little packets of light that actually carried that energy were called photons. So for some reason, light was made up of a bunch of little photons, and each one of those photons carried one quanta of energy. So let's take a look at a couple of examples. So visible light has wavelengths that range from 400 nanometers to 700 nanometers. The question is what range of energies do these photons have? So all we really need to do is calculate the energy of photons with a particular wavelength. Now we know that the energy of a photon is given by this formula here. It's equal to Planck's constant times the frequency of the light. However, in this problem we weren't given the frequency of the light. We were given the wavelength. So we have to relate the wavelength to the frequency of light. Remember that the speed of a wave is equal to the frequency times the wavelength. So this means that the frequency of light is equal to the speed of light divided by the wavelength. If we plug this into the formula for the energy of a photon, we see that the photon has an energy that's equal to Planck's constant times the speed of light divided by the wavelength of light. So if we plug these numbers into a calculator, we see that the energy of the violet light is going to be equal to 4.97 times 10 to the minus 19 joules, and the energy of red light is equal to 2.84 times 10 to the minus 19 joules. And one of the things that I want to point out about these two numbers is that they are both extremely small. So this means that the energy of a photon is very, very small. So what this means is that the number of photons in any type of visible light is just extremely large, and we'll see that in this next example. So in this example, we're told that an FM transmitter produces electromagnetic waves, and the FM transmitter emits 150 kilowatts of light at a frequency of 99.7 megahertz. And the question is, how many photons were emitted by the transmitter every second? So we're told that the power of the light is equal to 150 kilowatts. Now remember, power is equal to energy per unit time. So the energy that's emitted in 1 second is equal to the power times 1 second. So this is the total energy of all of the photons that are emitted. Now each photon has an energy that's equal to Planck's constant times the frequency. So the total energy emitted by n photons is equal to the number of photons times the energy of every individual photon, which is Planck's constant times the frequency. So solving for the number of photons that were emitted, we see that this is equal to the power times 1 second divided by the energy of a single photon, which is Planck's constant times the frequency of the light. And if we plug the numbers that were given to us into this formula, we'll see that this is equal to 2.27 times 10 to the 30th photons. So in any type of detectable light, you're just going to have an extremely large number of photons. So let's take a look at a couple of examples looking at the photoelectric effect. So this first example says that zinc has a work function of 4.3 electron volts. And the question asks, what is the longest wavelength of light that will remove an electron from a zinc plate? Now remember that the work function describes the amount of work that you have to do to remove an electron from a metal plate. So the amount of energy that we give this electron has to be at least equal to that amount of energy for that electron to leave the metal surface. Also, remember that an electron volt is a unit of energy. It describes the change in the potential energy of an electron when it moves through 1 volt difference. So 1 electron volt is equal to the charge of an electron times 1 volt. So that's equal to 1.6 times 10 to the minus 19 joules. Recall from the previous example that the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength of light. So the larger the wavelength of light, the smaller the energy. So really, we're looking at the smallest amount of energy that we can give an electron so that it still is removed from the zinc surface. And if we think about this, the smallest amount of energy that you can give the electron is equal to the amount of work that the electron has to do in order to escape the zinc surface. So what we can do is we can set this energy of a photon equal to that work function, that 4.3 electron volts. So if we do this, we can calculate this wavelength, and we see that the largest wavelength is going to be equal to Planck's constant times the speed of light divided by the work function. And if we plug these numbers into a calculator, we can see that this is equal to 288 nanometers. So let's take a look at one last example. This example says that light with a wavelength of 350 nanometers shines on a metal surface and emits electrons. The stopping voltage is 1.25 volts. So the first question is, what is the maximum speed of the emitted electrons? And the second part asks, what is the work function of the metal? So remember that the basic idea behind the stopping voltage is that when you apply the stopping voltage, the electrons will just barely stop when they reach the other metal surface. So the idea is that you have these electrons and they're being emitted from this metal surface, and there's this electric field which is opposing the motion of the electron. And at the stopping voltage, the electron goes and just barely makes it here. So at this point, when the electron reaches the other metal surface, all of the kinetic energy that the electron had has been converted into electrostatic potential energy. So we can set the kinetic energy of the electron equal to the electrostatic potential energy. So we can say that that maximum kinetic energy that the electron has is equal to the charge of the electron times the stopping voltage. And of course, the kinetic energy of an electron is equal to 1/2 mv squared. So using just this formula, just by relating the kinetic energy to the stopping voltage, we can calculate the maximum velocity that the electrons had. So we see that this is equal to 2 E times the stopping voltage divided by the mass of the electron square rooted. And if we plug these numbers into a calculator, we'll see that this is equal to 663 meters per second. And the second part of the question asks us to determine the work function of the metal. So remember that the kinetic energy that the electrons have when they're emitted from the metal surface is going to be equal to the energy of the photon minus the work that the electron has to do. So we're asked to solve for the work function, so if I rearrange this, I see that the work function is going to be equal to the energy of the photon minus the kinetic energy that the electron has when it leaves the surface. And then finally, because I was given the wavelength instead of the frequency of light, I want to rewrite the energy of the photon in terms of the wavelength. So this is hc divided by the wavelength minus the kinetic energy. Remember, the kinetic energy is just equal to E times the stopping voltage. And if I plug these numbers into a calculator, I'll see that this is going to be equal to 3.67 times 10 to the minus 19 joules, which is also equal to 2.29 electron volts. And actually, one thing that I should point out about these types of problems is that the work that you have to do to remove an electron from most metal surfaces is usually on the order of an electron volt, so something like 1 or 2, 3, 4, something like that, electron volts. So if you're getting energies that are very, very different than that, if this isn't 10 to the minus 19 or 10 to the minus 18 or something like that, then chances are you've made some type of mistake. So this is just a good thing to keep in mind, just kind of a reality check. Whenever you do a problem like this and you calculate that work function, you should get something in the ballpark of 10 to the minus 19 joules. And if you've got something that's way bigger than that or way smaller than that, then you've probably made a mistake somewhere. So that's the last example that I want to look at about the photoelectric effect. And in the next video, we're going to look at something called the Compton effect, which looks just a little bit more closely at that interaction between photons and electrons.